Imagine a fan that doesn't need a plug, a battery, or even a solar panel. In a world dominated by electronics, there is a mechanical marvel that breathes life simply from a small flame. This is the kerosene oil fan, an invention that defies the modern need for a power grid. Today, we are going to look through its transparent glass casing to understand the incredible engineering happening inside. This fan doesn't just move air. It converts pure heat into mechanical motion using the principles of thermodynamics. Our journey begins at the base. As you can see in the diagram, there is a kerosene oil tank at the bottom. A cotton wick sits inside this tank, soaking up the fuel through capillary action. When we light this wick, it creates a controlled flame inside the burner or combustion chamber. Unlike a lamp where the light is the goal, here, the heat is the primary product. This burner is positioned directly beneath a specialized cylinder. The flame provides a constant source of thermal energy. In engineering terms, this is an external combustion engine, meaning the fuel burns outside the moving parts, making it safer and quieter than the engines found in cars. Now, let's look at the glass cylinder located in the center. Inside this cylinder is a precise amount of trapped air. This is a closed-loop system. When the flame heats the bottom of the cylinder, the air molecules inside begin to vibrate violently. According to the laws of physics, when gas is heated, it expands. This expansion creates pressure. That pressure pushes against a piston, forcing it upward. This is the power stroke. However, for the fan to keep spinning, that piston must come back down. This is where the cooling mechanism comes in. As the piston reaches the top, the hot air is moved to a cooler part of the engine, often assisted by the fan's own breeze, where it rapidly cools and contracts. This contraction creates a slide vacuum, pulling the piston back down. This rhythmic push and pull is the heartbeat of the fan. How does an up and down motion turn into a spinning fan? This is where the drivetrain and gear system comes into play. The piston is connected to a crankshaft. Just like the pedals on a bicycle, the crankshaft converts the linear, straight motion of the piston into a circular, rotary motion. In the model, you can see the intricate brass gears. These gears are essential for two reasons. First, they manage the timing of the engine, ensuring the air moves between the hot and cold zones at the exact right microsecond. Second, they can be used to increase the speed, through a specific gear ratio. One slow stroke of the piston can result in multiple fast rotations of the fan blades. This allows the fan to reach high speeds even with a small flame. Finally, we reach the top, the fan blades. As the gears spin the central shaft, the blades begin to cut through the air. But there is a clever secondary function here. As the blades spin, they don't just blow air at you. They also blow a small amount of air across the top of the engine. This helps keep the cold side of the cylinder cool. Without this constant cooling, the temperature inside the engine would equalize. The pressure difference would disappear, and the fan would stop. It is a self-sustaining cycle. The hotter the flame, the faster the fan. The faster the fan, the better the cooling. And the better the cooling, the more power the engine produces. The kerosene fan is a masterpiece of the Stirling Engine design. It represents a time when engineering was about harmony with physics rather than reliance on complex microchips. It is silent, efficient, and virtually indestructible because it has no electrical components to burn out. By simply looking through the glass, we see a beautiful dance of heat, air, and metal, a reminder that sometimes, the oldest technologies are still the most fascinating. Next step, do you want me to translate the same text into another language, or would you like to add some background music suggestions for the voiceover?